Alrighty, can everyone see the shared slides?
Yes, I can see it at least.
Okay, cool. Yeah, so I'll be talking about better and simpler learning augmented online caching. So to start off, I'll first talk about just the broader question of online algorithms with ML predictions. And so online algorithms are all about decision making under future uncertainty. And so today we'll see this idea of online algorithms with ML predictions applied to the specific problem of caching. But more broadly, we can think of using ML predictions to reduce the future uncertainty for online algorithms via learned predictions. And so how this might look is that given a certain online problem, we can train an ML model to predict future inputs from past inputs, perhaps based on historical data. And then using this trained model, we want to be able to use it to guide our online algorithm when it makes its decisions. And so for caching, these decisions might look like, predictions for when each page will arrive in the future. And so you want to use this information about the future to somehow make better decisions. And so in this framework, we typically want to show results of the form. If the predictor's error is at most eta, then our competitive ratio is at most C of eta for some function C. So this general framework of online algorithms with ML predictions has received quite a bit of attention recently and has been applied to not only caching, but also scheduling, metrical task systems, and so on. Yeah, so next, I'll elaborate a bit more on this goals, where we want predictor's error to be at most eta, and then showing that the competitive ratio is at most C of eta. And so we generally want to have sort of the best of both worlds when we design algorithms like this. We want to get the good performance of ML when the error is low. So we want the competitive ratio to be much better than what one would be able to get with traditional worst case approaches. And so ideally this is close to 1 when eta is close to 0. And also we want robustness in the worst case sense. And so this would be identical to the typical worst case analysis that we consider in online algorithms. So we want there to be a gamma such that C of eta is at most gamma for all eta. And so this picture here provides sort of a stylized image of an ideal C of eta. And so in this talk, I continue the study of learning augmented online caching. And so towards this, I provide two results, an upper bound and a lower bound. And so for the upper bound, I show that combining this naive algorithm called blind oracle with some typical worst case algorithm for online caching, such as LRU or marker, actually gives an improvement on the state of the art. And so although this improvement is admittedly slight, one contribution of this upper bound is that it's quite simpler than the existing approaches. And so instead of sort of an ad hoc design of the algorithm, I show that simply using online learning to combine blind oracle with a worst case algorithm actually works quite well. And so along this message, the lower bound shows that combining blind oracle with LRU is optimal among all deterministic algorithms for this learning augmented online caching problem. And so actually, this simple scheme of combining two algorithms with online learning actually can give you an optimal algorithm, at least in a deterministic setting. So in the remainder, I'll quickly describe the model as well as my deterministic upper and lower bounds a little more formally. So in the online caching model, here, this is the classical setting where we want to serve a sequence of page requests, sigma 1, sigma 2 through sigma n, and we want to do so while maintaining a cache of size k. And so in this problem, we assume that each page has to be served from the cache, but that the cache can have is that of size k, so it can hold at most k pages at any given time. So if we have a cache miss, then we have to pay unit cost to bring our page into the cache, and otherwise serving a cache page is free. And also, if we have a cache miss and the cache is full, then we have to choose a page to evict, which is where the decision making comes from. So in a paper at ICML 2 years ago, Lycoris and Vasilevsky augment this model by adding to each page request a prediction sigma I of when the prediction hi of when the requested page sigma I will next be requested. And so they defined an error metric eta that is L1 error. So it's the sum over y of the absolute difference between hi, the predicted next arrival time, and yi, the actual next arrival time of the requested page sigma I. And so recall again that in the setting, we want to design algorithms with good consistency and robustness. So when eta is small, we want the competitive ratio to be much less than, like log k. And when eta is large, we will still recover the O of log k guarantee that worst case competitive analysis gives us. And so, so more formally, here are the theorem statements for the deterministic upper and lower bounds. And so we get this O of 1 over k times eta opt dependence on the error eta. And then it turns out that this dependence of 1 over k times eta over opt is optimal up to constant factors. So there exist inputs for any deterministic algorithms, there exist inputs that require this competitive ratio. And just as a quick note, for the randomized case, we simply replace the minimum, the log k in the k in the minimum, the log k. Yeah, that's all I had prepared. Thank you everyone for coming, and if you're interested in learning more, there's always the online presentation as well as the full version. Yeah. Happy to take questions now.
Okay, thanks a lot. So the randomized simply gets then a log k, you stated? Did I get this correctly?
Yeah, so for this deterministic algorithm, the competitive ratio is the min of this 4 over k times eta over opt in k.
Okay.
And
so
then
we have the minimum of log k.
Yeah, so it's the min of this and log k. Yeah.
And the lower bounds also work for this, or?
So there isn't as tight of a lower bound for the randomized case. So that's actually still an open question of seeing, if you can tighten the analysis for the randomized case. But
okay.
But yeah, so in a previous work, Rohatgi has a lower bound for the randomized case. That's minimum of log k and log of 1 over k times eta over opt.
Okay, thanks. Yeah. Okay, so the next speaker is Uwe Gabani, who will be talking about parameterized metrical task system, and this is a paper, this joint work with Sebastian Bubeck.
Thanks. I'll just share my screen, or at least attempt to do that. Can you see this?
I can see it, yes.
Okay, good. So hopefully everyone can see this. Okay, so this is a paper about metrical task systems, and I want to explain what metrical task systems are. So it's a model for online computing, fairly general. It captures many different, more specific online problems. In the setting, we have one server that moves in a finite metric space of endpoints, starting from some initial state S0. And it encounters a sequence of requests, row 1, row 2, and so forth. Each request assigns a service cost to each of the states in the metric space. And the service cost is either positive or plus infinity, where plus infinity means that the state is excluded from serving the current request. Now, in response, the algorithm has to has to choose a state in which to serve each request. So the response is just a sequence of states, S1, S2, S3, and so forth, where Si serves the request row I. And there is a cost associated with serving requests. So the cost is composed of two terms. One term is the movement cost. So if we serve state I in, if we serve request I in state Si, we have to pay the movement cost of moving from state Si minus 1 to state Si. This could be 0 if it's the same state, or higher than 0 if these are different states. And then after moving, we need to serve the service cost at the current state for the current request. So that's row I of Si. So this is the model. And quite a lot is known about this model. So it was introduced by Borden, Lineal, and Sachs in the early days of online computing. They already had tight bounds for the deterministic case. So we're measuring everything in terms of competitive ratio, and I'm talking about the best possible competitive ratio that can be achieved in any metric space right now. So in any metric space, you can get, there's a deterministic algorithm that gives a competitive ratio of 2n minus 1. N is the number of states. And this is tight, so there is a matching lower bound. As far as randomized competitive ratio, and here we're talking about randomization against the oblivious adversary. So in this case, there is a small gap, or relatively small gap. Very recently, Bubik et al. Showed an upper bound of order log squared n in any metric space. And it's been known for a while, following the rather long sequence of papers, culminating in 2 papers of Bartal et al., that the randomized competitive ratio is at least omega of log n over log n. And in fact, for some metric spaces, theta of log n is known. In fact, all of these metric spaces are hierarchically separated trees or specific versions of them, such as uniform metric spaces. And this is conjectured to be the truth in every metric space. But right now, this gap is still standing, and no one knows how to improve either the upper bound or the lower bound. So this is what's known in general. And now we come to the question that we asked. So we were intrigued by the fact that in many special cases of metrical task systems, actually much better bounds are known. In fact, often bounds that don't depend on the number of states at all. And you could ask why are special cases of metrical task systems much easier than general cases? So if you want to answer this question sort of in a rather general way, you're looking for a parametrization of metrical task systems that may explain better bounds. And the parametrization that we were looking at is a very simple parametrization. We were looking at the number of different requests that could occur in the request sequence. In fact, once you have n requests, you're down to, I mean, the lower bound kicks in. This is only interesting if the number of possible requests in the sequence is much smaller than the number of states in the metric space. And there are several motivations for this. I'll get to that, to the second motivation on the last slide. Here I want to talk about our results. So I'll just survey our results very briefly and then conclude. And then if there's any time left, you can ask questions, or otherwise look at the more detailed talk, the pre-recorded one. The interesting thing that we discovered is that the answer here depends on the metric space, and this is true even for HSTs. So even for the very simple metric spaces that are responsible for both the lower bounds and the upper bounds. So in particular, for uniform metric spaces, it turns out that for deterministic algorithms, in fact, this restriction of the number of possible requests enables much better bounds than are known in general. So the bounds are roughly a little bit more than linear in the number of possible requests. On the other hand, when you look at the randomized competitive ratio, the lower bound kicks in even for request sequences that consist of just 2 requests. So the only thing here is which of the 2 requests you encounter at any given time. That already enables a lower bound on uniform metric spaces of omega log n, and that's tight because in general you have an upper bound of log n for uniform metric spaces. Now, when you go up to 2-level HSTs, even the deterministic improvement vanishes. So for 2-level HSTs, even for 2 requests, both the deterministic case and the randomized case, you already get the worst lower bound asymptotically, the worst lower bound known for the general case. So for general metrical task systems, this parameterization only helps in the uniform case and not beyond. Now, we also considered a somewhat more restricted version of metrical task systems that's called metrical service systems, or subset chasing, where the service cost is either 0 or infinity. So you're actually chasing subsets of the metric space rather than general service cost. And here, the situation is different. So in fact, for any level HSTs, or at least we know this for 1 and 2 levels, and for higher levels, situation is a little bit murkier. So you get an improvement for both the deterministic and the randomized competitive ratio, but in fact, this improvement for small m does not distinguish between the deterministic and randomized competitive ratio. So for uniform metric spaces, for very small m, you get the same behavior in the deterministic case and the randomized case. It's linear in m. For 2-level HSTs, both the deterministic and the randomized competitive ratio are again in the same ballpark of being exponential in m. And the randomized lower bound carries over to a higher number of levels. So it's going to be double exponential for 3 levels, triple exponential for 4 levels, and so forth. And of course, this is meaningful only for m that is very small compared to n. So this is it. I just want to conclude. Ignore the first line here because I didn't actually show you how the bounds are derived for shallower HSTs. But here are some open questions for metrical service system, for instance. Here are some very simple questions that are not known. What happens with infinite metric spaces? For instance, can we even get a another very simple case is a weighted star.
We couldn't hear you for a moment.
Oh, sorry.
I couldn't.
So I'm asking the following very simple question. You have the continuous line, so it's an infinite metric space, and you know you have a sequence that consists of a sequence of three concrete subsets of the line. Can you achieve that you're chasing? Can you achieve finite competitive ratio, or does this force the algorithm to an infinite competitive ratio? Another very simple situation that we don't know how to resolve is an arbitrary weighted star. So again, a very simple metric space. Is the deterministic competitive ratio for m requests m or exponential in m? Then I wanted to mention this issue of leaky randomness. So as we all know, or as those who work on online computing know, randomness against the oblivious adversary is used to hide the algorithm's position. Now, what happens if the algorithm is leaky? So it leaks information to the adversary, and this information is leaked adversarially. So the lower bound on metrical task systems on two-level HSTs shows that even leaking one bit of information kills randomness, because the deterministic lower bound only needs to know which one of two requests needs to be requested at every given time, and that only requires one bit of information. So this is an interesting question in general on online computing, whether or not leaky information, how much does leaky information hurt you? And of course, the general question here is, can we find a better parameterization than the one we proposed? So I'll stop here. I hope I'm not.
Okay.
Too much.
I think it's fine because the next slot in the session is not filled. I think this was the last talk of the session, according to my list.
I guess I'm over time a bit.
Okay, I just want to announce maybe, so if you want to attend the invited talk, then you should, I think, go to this link here. So that's a Zoom session for random. And this invited talk, I think, is going to start at 9 a.m. Pacific Daylight Saving Time.
Right, after this session. So we can finish this session and then move to the invited.
Okay, but at least in my list, there is no additional speaker in this session. Or do I have, is my list wrong?
There should be one more talk.
I do have a slot, but there's no.
I see another talk in this session.
Okay.
Learning lines with ordinal control.
Fan, who seems to be here, is supposed to be another speaker in this session.
Ah, yes. Okay. So, okay. Oh, I missed that. Okay. 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 So, So then we will go to the next talk by Born Fan, learning lines with ordinal constraints.
Okay, I'm going.
Yes.
I'm going to share my screen.
Okay. Sorry, I got this mixed up. And now I lost my.
Can everyone see my screen?
I cannot see it yet. Now I see it.
No. Oh, okay. How about now?
Yes, I see it.
Okay. Hello, everyone, and thank you for being here. I'm Bo Han, and today I will briefly introduce our paper, Learning Line with Ordinal Constraints. First, I would like to show you what's the problem we want to solve. Given any data points and given a data set and also several constraints about the data point, this constraint is formed by a triple, and it will encode the information, proximity information. Like one point is more closer to another point than the third. We want to build a mapping to a real line that satisfy as many possible as possible of the original constraints. Formally, we want to compute a mapping F from N to R, such that for any triple constraint U, V, W, we want to have the mapping that FU is more closer to FV than to FW. And we refer to this problem as a learning line with ordinal constraints. Here, we only consider the dense case. The dense case means for any triple UVW in T, either UVW is in T or UWV is in T. In general, there's no embedding that satisfies all the constraints in the LLOC problem. Here, the general case means that even the optimal solution only satisfies 1 minus epsilon fraction of all the constraints. But we give the algorithm that for any instance of LLOC that admit a solution satisfy 1 minus epsilon fraction of all the constraints, we can output a solution that satisfies 1 minus big O epsilon to the power 1/8 fraction of all the constraints in a feasible time. This is given by our theorem 1. Before I talk about our general case, I would like to show you a simple algorithm for the perfect case. The perfect case means we can find a solution that satisfies all the constraints. It has 3 steps. First, we guess the point P in the optimal solution that is mapped to the leftmost point in the line. The second step is to find the order of all the points in the line. This is done by using all the constraints in the form of Pij. The order is constructed by the sorting algorithm. After we construct all the orders, we need to adjust the distance of all the points by solving an LP. This LP is built by using all the information of the constraint, like except for Pij, and all the feasible solution of the LP would provide us the optimal solution that satisfy all the constraints. Based on the similar idea, in the perfect case, we give the algorithm for the general case that only 1 minus epsilon fraction of the constraint can be satisfied. For the first step is nothing but the same. We guess the point P in the optimal solution, who is mapped to the leftmost point. And then the second step, we also find the order of all the points. But this time, the things is more difficult, and we can't just use the constraint like Pij because some constraint is not satisfied. Here we use we find the order that is still good by construct a tournament based on the leftmost point, and then removes the minimum feedback offset, and then after we remove the feedback offset, we can have the topological order of all the points in the line. And according to this order, we have the third step, retraction and extension. Here, retraction means we group all the points consecutively by different bucket. And after we have the bucket, we convert the original problem to the weighted version of learning a line of ordinal constraint. And the weighted version can be solved exactly. After we got the exact solution of weighted version, we can extend the solution to the solution of original problem. And thus we can have the approximate algorithm for the general case. For the due to the time limit, I'm not able to provide the detailed analysis of our algorithm. If you are interested, you can refer to our longer version or our original paper. Thank you very much.
Okay, thanks a lot. So what would be interesting open questions here?
The interesting, of course, is whether we can deal with the problem of non-dense case. I mean, in the dense case, for any triple, either UVW is in T or UWV is in T, but in some case, we may not have this either or relation.
Okay, and then, okay, so if you don't have this much information, then you don't know what's
we
done.
may not able to follow the similar approach and solve the result.
Okay. Okay, thank you very much, and sorry for the confusion. Okay,
there's
so
a question on the chat.
There's a question on the chat.
By Karsnik.
Is there a concrete motivation for this problem? Did you get the question?
Could you repeat again? Sorry.
Is there a concrete motivation for this problem?
Concrete motivation. Because in a lot of learning problem, we have the we want to use some we want to use less information, and like in this picture, in this picture problem, we only have the proximity information, like one point is more closer to one point to another point. So we want to use as less possible as information to find a mapping to the real line.
Okay, thank you. Okay, so then, sorry for the confusion. So the invite